Okay, we'll get started. I left off on Monday, and I didn't get to the last section on the bias variance trade-off, and it was mostly an illustration of what the bias variance trade-off. This is kind of where I left off on Monday. And you know what I think I'm going to do is I think I'm going to record a separate video covering this bias variance trade-off, and I will not. I'll just encourage you guys to take a look at it, to take a look at these slides. I think they're kind of fun, but I'm just looking at what I have to cover, and I think I'm going to move on to my next lecture here. So I'll record a separate video that you guys can watch covering the last section in Monday's lecture. All right, so today what I want to do is I want to start taking a look at neural networks. Okay, we're gonna look at neural networks because it is we're going to use gradient descent, an optimization technique that we've already talked about, and that's used in neural networks. And so we're going to just start there, okay? So we'll start with a quick review of gradient descent, which is that we are trying to find some value of some, say, vector w, okay, that will minimize this function f, all right? So you've got a function, you put a vector in, and you want to minimize it. And I think if you started your homework, you're already working with this. And if you haven't started your homework yet, then I suggest you at least take a look and get started. And so we've got some kind of function, right? And in this case, it's usually like the loss function. We want to minimize the loss function. And the loss function, it depends on this vector w, okay? And what gradient descent is it's an iterative algorithm. You start off at some arbitrary location, w at time 0, w sub 0, and we want to iterate and improve that so that we're going to get to w at time 1. And ideally, if every step we improve a little bit, then we'll reach a local min at some point. Okay. So the answer for how do we select our next value is we take our current value w at time n, and then we're going to subtract off gamma times the gradient of f at w at time n. Okay, so you calculate the gradient of f at w time n, and then you just subtract off some, you multiply that by some constant gamma, and you just subtract that off, right? And so gamma can be any value. It's the learning rate. It just has to be a positive value. It could be huge, it could be small. And a couple lectures ago when we looked at gradient descent, we saw, if you pick it too big, you can get this jagged kind of pattern. If you take it too small, then you're going to have this very slow convergence. It's going to take a lot of steps and things like that. So that's kind of where we're going to start here. Okay. And so now I will introduce neural networks. Okay. There are a couple playlists on YouTube that absolutely you need to watch, especially this one, this Welsh Labs Neural Networks Demystified. Watch that playlist because the example that I'm using in today's lecture is based largely off of this. There's another series of videos called 3 Blue, 1 Brown, and they are also very good. So be sure to watch these series of videos here. Okay, so I don't know if you guys have heard of neural networks. I'm pretty sure you've heard of a neural network, but maybe you're not quite 100% sure exactly how it works, okay? As far as this class goes, we're gonna look at the simplest, most basic kind of neural network. There's lots of stuff, okay, out there, but we're gonna just look at the most basic one, okay? Neural networks have technically been around for a very long time. Well, I don't know how long is long, but they've been around since the 1970s and 1980s, okay? But they've gained a lot of popularity in kind of the 2010s, all right? And that's because the computational power required for neural networks have been, has greatly increased, allowing neural networks to be applied to these massive data systems, okay? Neural networks are frequently used in kind of image recognition systems, and they power a lot of artificial intelligence technologies. And I like to cover it because I think they're neat, and they are a good application of gradient descent, which we talked about, okay? And basically, what a neural network does is it's a function, okay? It's a design. It's a way for us to design a function in that you have inputs and it produces an output, okay? At the heart, that's what a neural network is. You have a function that takes inputs and creates an output, okay? Except what happens inside the function is just maybe a series of computations, okay? A series of computations, so it's gonna do stuff. And the inspiration for the neural network is a brain, okay? And we don't fully understand how the brain works, but we do know that inside the human brain, you've got neurons, and each neuron is connected to other neurons through these synapses, okay? So your brain has neurons and it's got synapses to connect to other neurons. And basically what happens is when you are thinking, when you are speaking, when you are doing stuff, you know, a neuron fires and it travels to the other synapses, and the travels, you know, to the other neurons. And depending on the signals that, you know, a particular neuron receives, it's either going to activate and send out another signal. And you have this huge kind of interconnected, I guess, network of brain cells, of neurons, okay? And so in a biological brain, a neuron receives input signals, and depending on the signal and the neuron's function, the neuron may then send a pulse, or what they call an activation potential, to other neurons, okay? And so what we're gonna do is we're going to create basically a computer version of this. We can call this an artificial neural network. And it's gonna consist of nodes, and those nodes will receive input values. And depending on the input value, and the node also has what's called an activation function, the node will then send a new output value to other nodes, okay? And so I'm going to follow the example that comes from Welsh Labs, okay? And it's a silly example. The input matrix has two columns, okay? We're going to have an x1 and x2. So this will represent hours of sleep, and then the second column will be hours spent studying, okay? So, and then, and based on that, we're going to try to predict the exam score, okay? And so the exam scores are 75, 82, 93. So this one says you slept 3 hours, you studied 5 hours, or the person, whoever this is, studied 3 hours, slept 3 hours, studied 5 hours, and scored a 75. The next day they slept 5 hours, studied 1 hour, and got an 82. And this one they studied 10 hours, slept 10 hours, studied 2 hours, and got a 93, okay? And obviously we would probably want more rows of data, but just to keep this simple, we've got 3 rows of data, n rows, so n is 3, 2 columns in our X matrix, and 1 column for our outputs Y. And what we want to do is we want to create some kind of function that will take in 2 values in X and output 1 value of Y. Okay, it's going to take in 2 values X, 5 and 1, and output 82, take in 2 values 10 and 2, and output 93. Okay, and so that's how we're going to start up. Okay, when we do this, we're going to start with what's called an input layer. Okay, the neural network starts with an input layer and is going to end with an output layer. Okay, so because we have 2 columns in our X matrix, okay, our input layer will have 2 nodes, one for each variable. It's going to have an input for X1, hours of sleep, and an input for X2, hours of study. Okay, and then it'll pass through the network, and at the very end of the network, okay, the output layer has 1 variable, okay, which is going to be the exam score, all right? And so the output layer will have only 1 node. Now, you can have other kinds of neural networks where you have more than 1 node in the output layer, but right now, we're just taking inputs. We've got 2 inputs to go in, and each of those 2 inputs should map to 1 output, okay? But the neural network, what makes it a neural network is that it's going to have at least 1 hidden layer, okay? You can have more than 1 hidden layer, but we're just going to have 1, okay? And for our simple example, we're going to have 1 hidden layer with 3 nodes, okay? These choices here are arbitrary. The choice of having 1 layer with 3 nodes is arbitrary, but I've used, I chose these numbers. Well, it's mostly to keep it simple, okay? And I'm choosing these because that's what the Welsh Labs video did, and so you can watch the video tutorial as well. But we're gonna look at that, okay? And the arrangement layers is gonna be you start off with the input layer, and then you go into a hidden layer or multiple hidden layers, and then you end up at the output layer, okay? And every node, this is the important thing, is that every node in each layer is connected to all the nodes in the next layer, okay? At least in our simple, we'll call this a fully connected neural network, okay? In other, if you took a course on neural networks or something, you can have different designs, okay? But this is what our picture looks like, okay? We've got an input layer, all right, which has, is going to be basically the column X1 and column X2, okay? And this has there's n by 1 values in X1 and n by 1 values in X2, okay? And this will be hours of sleep, hours of study. And this X1, we've got 3 nodes in our hidden layer and 1 node in our output layer. And X1 is connected to all 3 nodes in the hidden layer, okay? And X2 is connected to all 3 nodes in the hidden layer, okay? So each node here is connected. So there's a total of 6 connections between X1, or between the input layer and the hidden layer, right? We've got 3 coming out of X1 and 3 coming out of X2, okay? And then in the hidden layer, each of these nodes are connected to the output layer. There's only 1 node in the output layer, so each one only has 1, okay? And so our output layer has dimension n by 1, because we've got n inputs, n rows of input, and so we're going to have n rows of output, all right? So this is kind of the diagram of what our neural network might look like here. Okay, and this is about as simple as we can get for a neural network here. Okay, and so I don't know if you've heard of this idea called deep learning. Okay, and the idea behind deep learning is that you can have a lot more than 1 hidden layer. Okay, you might have hundreds of hidden layers, okay? And if you have hundreds of hidden layers, okay, basically each hidden layer would be connected to all the nodes in the next hidden layer, and all of those nodes would be connected to all of the other nodes in the next layer, and you'd have lots and lots and lots of connections, like on the order of millions of connections, and millions or even billions of connections, and we would call that like a deep deep neural network or a deep learning model, okay? And they've been shown to be incredibly powerful. So for example, there's been this data set called ImageNet, which has 14 million images with thousands of possible categorical labels. So it'd be kind of like, this is a picture of a, and it's not just a picture of a dog and a horse and a cat, but it'd be like, this is a picture of a pit bull. This is a picture of a bulldog. This is a picture of a greyhound. And there's thousands of possible categories. This is a boat and an airplane and a car and I don't know, all sorts of stuff. And for a long time, people thought, it's not going to be possible to get a computer to recognize all of these things. But it's already been 5 years. But I remember when this happened in 2015, a deep convolutional neural network, or we're not going to learn this deep neural, how to do this, but the deep convolutional neural network surpassed the human error rate for labeling images, okay? So because there's like thousands of categories, I think people would achieve like, 96% accuracy, 95, 96% accuracy, because it's kind of tricky to be able to correctly identify exactly which category it is out of 1,000 categories, okay? But, and so in around 2015, the computer was able to beat that, okay? And the performance continues to improve, and so now things are being done on kind of real-time video. A lot of the self-driving car stuff, a lot of that is powered by neural networks. So here's just a video. We're not going to get to this, okay? I just want to kind of click on this and show you a little video, but we're not gonna learn how to do any of this kind of stuff. We're gonna just start off with the most basic, but it serves as a starting point, and you can okay. The link is the link broken? Did something happen? Oh, great. Adobe Acrobat is not responding. Okay. All right, that's too bad. Okay, let me see. Let me open up my document again. Let me see if I can just copy and paste the oh goodness. I want to show you the video because I think it's neat. So. And so this is going to be a video showing basically a neural network running in real time on video being streamed while a car is driving. And what the neural network is doing is that it is trying to recognize the objects that appear in the scene. Okay, I guess we have to wait for a commercial first. Okay. So so here is this is video of a car driving, and as it's driving down the street, it is superimposing kind of these shadows to say it recognizes this as a car. These things over here are people. This is a bus over here. It's recognizing this up here as a traffic light, and it's just as the video feed is going in, it also recognizes this is traffic light, these as people. whatnot. It's recognizing all of this to kind of get a vision of what's happening on the street. Okay, and anyway, that's powered by a neural network. Okay, so anyway, all to say, we're not going to get there, but we're going to learn the most basic form of a neural network, which I still think is pretty neat. But here's one thing to note about neural networks. They're good at predicting things. They're good at kind of performing some kind of task. But if you want interpretability, right, if you want to be able to understand the relationship between variables, neural networks are not good at that, okay? Neural networks, basically, after you train the neural network, you have no idea what each node does, okay? It's kind of like neuroscience, all right? People have been studying the human brain, but they still don't fully 100% understand how everything inside the human brain works, okay? And and I was listening to this one person talk about neural networks, and they said, you know, once neural networks become even more ubiquitous and used all around, like there might be another field developed of basically neuroscience for neural networks. Okay, in that you would look at a neural network and you would try to study each node inside the neural network and try to understand what it's doing. It's just kind of funny because nobody knows really how what's happening inside the neural network. Okay. Anyway, so this is the network that we're going to try to set up here, and so let me just show you how we go from inputs to our output. Okay. And everything is done in the language of matrices. Okay. So again, we gotta be comfortable with doing matrix operations here. Okay. And so let's just take a look, okay? We have our inputs, we have our outputs, and basically what the neural network is gonna do, what you are able to alter and mess around with when you work with a neural network are the connections from one node to another, right? You are going to alter what we call the weight connections, all right? So is X1, does that have a strong connection to this node, or does it have a strong connection to this node? Does X2 have a strong connection to this node and a weak connection to this node? Things like that. Basically, in our network, we've got 6 connections to play with in the layer between the input and the hidden layer. And then we have 3 connections to play with between the hidden layer and the output layer. Okay, so there's each of those arrows is a connection, and we can alter the weight of those connections, which is basically how important that connection is. All right, and then the 3 connections between the hidden layer and the output layer, again, we can configure those weights. And so when we talk about training a neural network, all right, training a neural network is all about trying to figure out the values to use for these connections. Okay, so that we have 9 weights that we can mess around with. Okay, we have 9 weights that we can mess around with, and we're trying to figure out basically what coefficients we should use for those 9 weights. Okay, and that can you know, that's what we are going to do. Okay, so I've labeled all of these connections, and so we're going to call the weight matrices W. Okay, the weight matrix, the weight value between connection node X1 and inside the hidden layer, we're going to call the hidden layer values Z. Okay, from this value in the hidden layer Z is going to be basically we're going to take X1 and we're going to multiply it by the connection going from node 1 to node 1. So that's going to be weight 1, 1. Okay, and then the connection that goes from down this arrow is going to be weight 1, 2, because it comes from node 1 and it ends at node 2. And then this red one that goes from this the first node, node 1 to node 3, is going to be called weight 1, 3. Right? And then likewise, we've got node weight 2, 1 to go from the second X node to the first hidden layer node, okay, this purple line goes from the second node to the second node, so that's weight 2, 2. And this one, which goes from the second node to the third node, is weight 2, 3, okay? And then all of these, there's only one node in the output layer, which we call Z, okay? So the hidden layer, because it's the second node, is going to be called Z2, okay, or Z super 2, and over here we've got a node here, and this is going to be called Z super 3. Is this kind of like Markov chain Monte Carlo? Gavin asks. I would say it's quite different from Markov chain Monte Carlo. Markov chain Monte Carlo uses a Markov chain. The next state of values depends on the current state, and it's a Monte Carlo method in that you do a bunch of randomizations to get your values. But this, I would say, is quite different in that you know, there's a bunch of connections and maybe there's arrows in common, but I would say it's a bit different here. Okay, so so I've labeled each of these connections. So here, going from the first hidden layer node, Z1, in Z super, I guess Z super 2 sub 1, going to Z super 3, and there's only one there. That's going to be weight 1, 1. Okay, and it's weight super 2, okay, to indicate this is our second weight matrix. Okay, so all of these in this first set of weights, these are all W super 1 to indicate it's our first weight matrix, and then everything in our second weight matrix will be W super 2. Okay, so there's superscripts and subscripts. There's a lot of scripts going on here, and so take your time as you're gonna have in your third homework assignment, okay, you're gonna have to do some neural network stuff. Take your time through them, okay? Make sure you know where, what everything should be labeled, okay? So, so this is what we have, okay? We're gonna organize these into matrices, okay? So I've got W super 1, that's the weight matrix that goes from X to the hidden layer, okay? Going from X to the hidden layer. And I've tried to color code these, okay? I've tried to color code these accordingly, okay? That has, it's 2 by 3, okay? Because we have 2 X inputs and 3 outputs, all right? So we're gonna take our inputs X and our outputs, and so it's gonna be 2 by 3, and it's arranged this way, okay? So the first, the X1s will get kind of multiplied across the top row, and then the X2s will get multiplied this. Would it be possible to go back to the slide with the chart or the diagram for a second? Yeah, this is what we've got, okay? I've also, I think I've uploaded this to CCLE, at least this version of the things. You can kind of follow along there as well, okay? So we've got these 6 values, okay, for these weight matrices are arranged in this W1 matrix, okay? And then the second weight matrix is going to be W2, W super 2, okay? And it's got 3 rows and 1 column, okay? Because we've got 3 rows or 3 nodes in the hidden layer and 1 node in the output layer, okay? So it's basically how many nodes going in by how many nodes going out, okay? So we've got 3 coming in for weight 2 and 1 going out. So what's going to happen, okay, this page, maybe it looks a little scary, but it's not, okay? So if you think about your input matrix X, your input matrix X has n rows and 2 columns, okay, right? So we had 3 days of exams, but each thing we had 1 column for hours of sleep and 1 column for hours of study, okay? And however many observations we have is going to be n. So if I take my input X matrix and I multiply it by my weight matrix W super 1, okay, W1, and I multiply that out, the output is going to be n by 3, okay? We're going to have a matrix with n rows, so same as the number of observations, times the number of columns in our hidden layer, okay? We're going to get n by 3. And so, so if we multiply this out, this is what we get. And again, Man, it was a lot of work to color code all of these weights, but I'm hoping by color coding them, you can kind of see what's happening. So we're going to take our inputs, for these values, it's going to be this times this plus this times this, and that's going to give us the middle column value, and then the last column value is this value times this value plus this value times this value, and we're going to get this one, right? So you kind of do your matrix multiplications, and so in our data set, we got our n is 3, okay? But in an arbitrary data set, you're going to have n rows, okay? And so this is what you have. So we're at n by 3. How are we doing? Are we doing okay? Is this okay so far? Give me a green check mark if you're doing good. Let me also give you the answer to the first quiz question. Today, the first quiz question, the answer is B as in boy, okay? B as in boy for the first quiz question. B as in boy for the first quiz question. Okay. Well, 2/3 of you gave me green checks. Anybody know? Everyone else is doing okay? I don't know. No red X's. So I guess that's a good sign. All right. So this is where we get. Okay. Now we're going to apply to the z. Okay, to introduce, I guess, a bit of nonlinearity, or to simulate this activation function. We apply some kind of function. Okay, and when you apply the function, you apply it element-wise, okay? So this matrix down here is called Z. It is n by 3, okay? This is Z2. It has n rows and 3 columns, okay? Because our hidden layer has 3 nodes in it. So we've got n observations, 3 columns, and we're going to apply a function element-wise, okay? So we apply the function element-wise. So when we apply the function f to an n by 3 matrix, we're going to get also each element just gets put into f. So f is just a regular old function, one input, one output, okay? So it could be something like the square root of x or x squared, or in our case, it's going to be what's called the sigmoid function, but your activation function is technically allowed to be, pretty much whatever you want it to be, okay? And we apply it to each element, okay? So we apply it, so it doesn't change the shape of the matrix Z, it just changes the values inside. And so after we apply it here, it becomes our matrix A2, okay? And so what we do in here, I'm going to use the sigmoid activation function. This is basically the logistic activation function also. It's the same thing. And what this will do is by doing 1 divided by 1 plus e to the negative t, okay? When t is a very large positive value, okay, e to the negative very large positive becomes 0, and you're going to get 1 over 1. And so that will be the largest value you can have. And then when t is a very large negative value, e to the negative t will become a very large number. And so it's going to become like 1 over something approaching infinity. And so that will go from 0, okay? So this will take any values on the domain for t, which goes from negative infinity to positive infinity, and it kind of squishes it down to the range 0, 1. Okay, and this is basically what the activation function looks like. Whatever numbers you had, so I think it's going from like -8 to 8 or something, it's going to squish it all down between 0 and 1. Okay. Is that a reason that we picked a sigmoid shaped function? Is there a reason? So this was kind of the classical activation function for a long time because it had outputs between 0 and 1, and that was believed to be a desirable trait. I would say it's frequently used, at least for introductions to neural networks, because of its classical value. But to be honest, it has fallen out of favor these days, okay? People don't like to use the sigmoid activation function anymore. And there's a whole bunch of different activation functions that you can use. A very popular one these days is the ReLU, the rectified linear unit. But then there's other versions, one called the leaky ReLU, and then there's the, hyperbolic tangent and whatnot. I'm trying to follow what was done in the video series, and I would still say the sigmoid activation function is still used, at least in the teaching of neural networks, probably largely in part because of its historical value. Now, maybe this will change one day, but that's what we've got. It used to be believed that it was good to always have your numbers kind of on some kind of set range, like from 0 to 1. But you know, now we have ways around it. Okay. Okay, so here's our neural network, and so basically we take our x, we multiply it by w's, and we get our nodes of z's. Okay, then we take our z's, we're going to apply the function, and I don't have, so basically the z's become a's, and then we're going to take the a's and we're going to multiply it by w's to get kind of our third z thing. Okay, so after we've applied the function to z, we get this matrix A. Okay, and we're going to multiply this matrix A by our next weight matrix W. Okay, and so in our case, A is n by 3, n rows, 3 columns, and W is 3 by 1, right? We've got 3 weights here, 1 output node, so we're going to arrange it 3 by 1. And so when you do this multiplication, you're going to, each element is the sum of this times this plus this times this plus this times this. Okay, you go, you know, the first element times the first element, second element times the second element, third element times the third element, but you're going to add them together. And so this whole thing collapses down to an n by 1 column. Okay, so we get n by 1. And so this is where we are. And then the last thing we're going to do is we're going to apply another function. Okay, we're going to apply the same activation function to this n by 1 column matrix. Okay, we're going to apply f to this, and this is going to create our outputs y hat. Okay, and so this is what we get. Okay, and that's how we go from inputs to some kind of output value once you have your weight matrices. So in summary, we take our input matrix, which is n by 2, we multiply it by our weight matrix 2 by 3, and this gives us an n by 3 matrix. We apply a function to z, okay, which is n by 3, and that's going to result in an n by 3. We take the resulting matrix A2, we multiply it by our second weight matrix, W2. A2 is n by 3, W2 is 3 by 1. The output's going to be n by 1. Then we apply a function, f, to this final output, Z3, which is n by 1. And that's going to give us our y hats, which are n by 1, okay? If you kind of nest all of these together, you can just say y hat is the function, the sigmoid applied to the sigmoid applied to x times w1, and the result of that times w2. Okay, so all of these things can be rewritten into just kind of one line here. It can also be left as kind of a series of operations. All right, is that feeling okay? I guess I might as well give you the second quiz question answer. The second quiz question answer is also B, okay? It's second quiz question answer is B as in boy. Okay, did we all get second quiz question? All right, does anybody have any questions? Any questions here? Type your questions in the chat, raise your hand. I hope this is feeling okay. If you watch the Welsh Labs series of videos, and I strongly, or actually I'm going to kind of require that you do, I'll put it as part of your homework. One thing it doesn't do is it does not apply bias functions. Okay, Mayo asks, can the function be any function, or are there some specific requirements? Technically, it can be any function as far as the activation function goes. There are certain functions that are more desirable and better suited for this, but there are not going to be things like this. Numeric example. I will not do a numeric example today. Okay, we won't have time for that. Okay, but I'll do a numeric example probably on Friday. Okay, but so today is just going to be a whole bunch of letters and matrices, and then we can do a numeric example later. Okay. Can you give us a general gist of what constitutes a good activation and what function what does not? Okay, read the Wikipedia article that I've linked in here on activation functions, and you can get a sense, okay? But basically today, if you're not sure what to use, the ReLU is probably a good choice, okay? Sigmoid, it's not so terrible either. I mean, it's not popular anymore, but read the Wikipedia article on activation functions. Okay, there's something also known as biases, okay? You can add what's called a bias, and that's basically to, so what we had before is we did x times w and we got our z's, but we can also add a constant, okay? A constant, beta 1, to each of these nodes. We're gonna add a constant here, b1. We can add a constant b2 to this node and a constant b3 to this node, okay? And then also, we're going to add a constant to each to the node here. Okay, so we can give we can add biases, and so basically what that's going to do is it's just going to shift the you know, when you do x times w, you get a certain value, and you can add a constant to either just shift it up or down the number line, and so it's just like having an intercept, but we're just adding a constant. Okay. The constant is going to be the same for each thing coming into the nodes, and so the matrix that organizes these constants in this case is going to be 3 by 1, and the matrix that organizes this constant is just going to be 1 by 1. Okay, and so in order to do this, okay, so you know there's one bias term for each node. So our matrix of biases for the hidden layer, which has 3 nodes, is going to be 3 by 1. Okay, and in order for the matrix multiplication and dimensionality to work out, you have to multiply the matrix of biases by a set of constants. Okay, and so we're going to create a matrix of just ones called J, and we're going to multiply J times my bias matrix transpose. So we're going to take the bias matrix transpose, we're going to, so that will make B1 transpose a 1 by 3 matrix, and J is going to be an n by 1 column matrix of ones, okay? And that will allow this to become n by 3, this will be n by 3, and the result will be n by 3. So let me just kind of illustrate what this looks like, okay? So when you have x, which is n by 2, and w, which is 2 by 3, this will combine to be n by 3, okay? What we have here is, because b only has, is a 3 by 1, I transpose it, okay, into a 1 by 3 matrix, and I multiply it by a column of ones in order to kind of make sure I can add the same set of b's to each observation. Okay, I've got n observations, and I want to add b1 to the first element of all of those things. I want to add b2 to the second element of all of those things, and I want to add b3 to the third element of all of those things. Okay, so this column of j's and b's is necessary in order for the matrix multiplication to work out, right? Because with all of this, the keys with matrix multiplication is that all the dimensions have to line up. Okay. You know, take your time working through these slides here. Okay. I tried to color code everything to kind of help you see where all the elements are going. Okay. And so that's a hope that this clarifies how the matrix multiplication works. Okay, so we do xw plus j times b1 transpose, and this is going to give us our matrix Z. Okay, you apply the same activation function to Z, all right, and that's going to give us an A. And so A, like before, is n by 3, and w2, our w2 weight matrix, is 3 by 1. And in the last case, we only have one node in the final output layer, and so we're going to add a B1 term, and there's only one of them, so our B1 term is a 1 by 1 matrix, okay? But again, I multiply that by a column a column matrix, a column of ones, which we're going to call J. This is n by 1. And so when I do this, this is going to become n by 1 matrix that I can add to everything. And so the result is also going to be n by 1. Okay, so when you do this, you kind of go across the first element times the first element plus the second element times the second element plus the third element times the third element. And that gives us A11, W11, A12, W21, A13, W31. And then we add on B1. Okay, and we add on B1 to every observation that we get. Okay, and so the result is going to be n by 1. And so if we summarize all of these equations, okay, we do x times W1 plus J times B1 transpose. That gives us Z2. We apply the activation function to each element in Z2, which is going to keep the dimensions the same. Z2 is n by 3, and A2 is still n by 3. And then we take that A matrix, A2 matrix, which is n by 3, and we multiply it by our W2 matrix, and we add on J times B2 transpose, okay? Technically, in our case, because B2 is just a 1 by 1 matrix, we don't need to transpose, but it's possible in the future you have a more than one node in the output layer, and you would need to do the transpose operation, okay? Then you would get the Z3 matrix, you apply the activation function to Z3, and that would give you your y hats there, right? And so again, if we nested all the functions inside of each other, this is what we would get, okay? And you can check all of the dimensions and they should line up correctly, right? And so this is what we call forward feed. You take the inputs, you will multiply it by a matrix, you apply a function, multiply it by a matrix, apply a function. And if you had deep learning neural networks and stuff, you would just keep going and you'd multiply by a matrix, maybe add a bias, apply a function, so on and so forth. And then finally you would get your output y hat, okay? So this is here just to show you how you go from your inputs x and then the weight matrices and possibly your bias values to get your output y hat, which we will use, okay? And so what we're gonna do next, is we are going to try to figure out how to pick our values for our weight matrices in W1 and W2, or our bias values inside our matrices B1 and B2, okay? And what this will do, in order for us to do that, is we are going to try to minimize the loss function, okay? So just like everything else, just like in ordinary least squares linear regression, you're trying to find your intercept and your slope that minimizes the loss function, which is the total squared error. We're gonna do the same thing. We're gonna pick, you can't call them intercept and slope, but you're going to pick, your W's, okay, so that this value, the squared loss, okay, which we're familiar with, the squared loss is as small as possible, okay? It's just that the way we find y hat is now complicated. With linear regression, it was simple. Y hat was just xw, right? It was just the x matrix times the w matrix. The w matrix had the slope and intercept. Now it's a little more complicated, okay? Y hat is now the result of this or the result of this. And so what we're going to do is we're going to do what we did before. We're going to take the gradient of this and use gradient descent to try to minimize this. Okay, that's it for today. This is your very first introduction to kind of neural networks, at least with a whole bunch of matrix multiplication. So again, get comfortable with working with matrices here. And we'll see you guys on Friday.